Thank you very much. Good morning, everybody. One final reminder is we will have our midterm on March 7, which is Friday. And the room is Salvatore 101. And if you are session 1, your exam will be from 4 to 6 p.m. And if you are session 2, your exam will be from 6 to 8 p.m. And the material, include today's lecture. Not Thursday's. Thursday lecture will not be included today's lecture. Okay, now let's continue our discussion from last time. We started looking at the different switching architectures, different excuse me, different switching architectures, and we said that we do have two types. We do have time switches and we do have space switches. Time switches, switches in time, whereas space switches, switches in space. Space switches do not switch in time slots. We looked at the two different types of architectures, shared memory, and the other one is called shared media. The data will be inputted, data in every time slot will be inputted, read into the memory, shared memory, and then what? Read from the memory to an outgoing time slot. And we said that in the switch to operate at a switching rate or speed at 2nr. Why? Because we assume that r is the rate of what? R is the rate of the cells incoming on each input, and we do have an input. And why is this one 2? Because during each time slot, they write into the memory and what? Read from the memory. So the switch needs to work much faster than each individual input. In the case of a shared memory, they are sharing a high-speed bus. All the lines are sharing. So as soon as you write into the bus, the other side or the destination will what? Will receive it. You don't need to have 2 cycles. It's just 1 cycle. So the bus speed has to be what? NR. Remember, at any instant of time, only one line can put what? Only one traffic from one incoming can what? Can put the traffic on here. Otherwise, there will be collision. Clear? So this one, when he works n times as fast as this one, they are what? Using the bus instantaneously. But they are not using the bus instantaneously. They cannot do that. It's one hour. Because the bus is n times as fast, it looks like as if they are what? They are using the bus instantaneously. Then we went into the what? Into the space switches. And again, as I told you, switch in time, just in space. And the first case that we looked at is what is known as a what? A single crossbar. We call it a crossbar, where the intersection of every incoming and outgoing link is to a cross point. This is a cross point. And remember what I told you last time. In every row and in every column, there should be only one cross point that is activated. So in this example, we have what? Communicating with 1, incoming 1 with 3. Users 1, user 3. So this one needs to be activated, connecting what? Incoming 3 to what? Outgoing 1. And this one, 1 is communicating with what? Outgoing 3. Clear? Communicating with each other. This is, by the way, a non-blocking switch. A non-blocking switch. What does non-blocking mean? Means any free output can be reached by what? By any input. Clear? As long as the output is free. Clear? Okay. And we saw that the complexity, which is the number of cross points, how many switches do we need? N squared, because it's an n by n switch. Then we look stage switch, a 3-stage switch. We divide, it's still an n by n, an input and output. But instead of building a single stage where we do have only one path, in here, incoming port to any outgoing port, there is only what? There is only one path, which means what? If this cross points, for example, or this cross points fails, then 1 to 3 will not be able to connect with each other. There is only one path. In here, we designed the network into a multiple stage. This one is a 3 by 3. Sorry, it's 3 stages, are space switches. We are not switching in times in here. Okay, so what do we have in here? And inputs and what? K out, the number of what? K is the number of outgoing this from this space switch. Clear? All of these are space switches. These are, how many stages do we have here? How many units do we have here? N by what? By N. Why it is N by N? Because everyone has N inputs. So if we have N by N, the total is how many? N inputs here. Clear? Total is N inputs. This is the mirror image of this one. So if this one is N by K, this one is K by N. Clear? Okay. Time that for this one to be what? By the way, how many paths are there from here to here? Going from here to here. How many possible paths there are? There are, how many units in here? K units. What? K paths. So for example, one path will be like this. Follow me here. This, then what? Did you get this or not? That's one. Can you zoom back please a little bit? Thank you. That's one path. And then what? Switching to here, and then what? Switching to here. Clear? Another one could be what? Could be this, and then what? All the way to here, and then what? This one, and then what? This one, and then what? This one. Are you following us? One more time. How many paths? There are K paths from what? Any incoming port, any incoming link to any outgoing. There are K. Okay, and we saw last time that for strictly what? For strictly non-blocking, K, which is the number of units in the second stage, K has to be greater than or equal to 2. And I explained this one to you last time. The worst case scenario is what? All of these are what? Occupied. If all of them are occupied, what does it mean? It means, how many of these do we have? Small n. It means n minus already what? Occupied. You cannot use it. Clear? To support this call. And the worst case scenario, all of these are what? Are occupied. Which means what? Another n minus 1 of these are used. So we need support what? To support the call from here to here. Clear? Okay. This is how you measure the complexity of a 3-space switch. The number of cross points. This one. Cross points do we have here? Here. How many cross points? N by what? How many cross points here? N by K again. Yes, this one is just a mirror image of this one. So what do we have? We have 2 N. How many of these do I have? N by N. N divided by N. So 2 times what? NK. This is the number what? NK is the number of cross points in here. I have N over N, and I multiply by what? By 2, because it's for this stage and this stage. Now, in the middle stage, how many do I have? How many units do I have? K units, and each one of them is how many? N by N by N by N, which is this one. And you get this. Now, if you substitute, then in other words, in its place of K, you put what? 2N minus 1, you end up with this. And when you take the derivative and you have to see the optimum value of N, you will see that the optimum value of N is approximately what is square root. And the complexity as compared to the single stage complexity is what? Is proportional to the what? Square of the size of the switch, whereas this one is what? Proportional to the what? To the what? 3 over 2, which means what? This one requires what? Requires more or less? It requires less than this one. Clear? Less than this. This is an example of a non-blocking switch that then we started looking at what? Time slot interchange. And again, this is time switches. In time switch in what? You do not switch in time. So this is what I have in a time switch. This is a time switch. I showed you this slide. This is a time switch. How many inputs does it have? Input. And how many outputs? One output. The input is slotted. So what? Slotted. Number of inputs in here, the number of time slots in here does not have to be the same as what? The number of time slots. Get this or not? Okay. So what are you going to do? You are, every one of these time slots is going what? The time slot content of the time slots is written, so is written sequentially into the memory, into the data memory. This is the data memory, so you have the following. These are the content of the time slots. This, for example, this content written where? Here. This content will be what? Written here. And this will be written in a sequential fashion. Yes? And read what? And read according to what? According to required connectivity. Okay, now we have a control. This is called what? The data memory. This one is called what? Control memory. This one pointing toward what? Location. This one does not care about what? The content of the memory. It's about what? The location. Clear the location, which means what? This one will provide what? Addresses. So for example, let's ask what? Time slot 1, you want to switch it to what? Time slot 3. So what do? 3. And 3 to what? 1. 3 to 1. They are talking with each other. 1, 3, 3 to 1. They are talking with each other. The time 1 to 3, the 1 is where? Stored in here. Yes, it will be written during this time location. Are you following me on that? When will it be read? When will it be read? When will this location be read? Be read during what? This time slot. So this is going to be switching in time. Now, by how many time slots? By 2 time slots. It got delayed by 2 time slots. So what do we do? Switches introduces what? Delay. Whereas the space switches does not introduce delay. Because space switch what? Time slots. Did you get this or not? So this one got read in here. How about number 3? Can I read it here? No, I cannot read it here. Why? Because this one has already what? Gone. This is time slot number 1. It has already what? Gone. So where will this one be switched to? Switched to what? To the first time slot in the what? In the next frame. This one will be switched in the first time frame. What comes after this one? This one frame. What comes after it? Second, fourth frame. Did you get this or not? This one will be switched in the what? In the first, second frame. Did it encounter delay? It also encountered delay. What is the maximum delay possible? Some delay a time slot can encounter. The maximum delay is just what? 1 frame before 1 frame duration. That's the maximum delay that you can encounter. Clear? Clear? Okay. Now, we can hybrids. Let's look at this and we try to calculate the complexity of switches. Complexity of switches is number of what? Cross points. Number of bits. Memory bits, both what? Both data and what? Now usually they divide this one by what? I need you to explain to you what does that mean when I say usually is divided by 100. The cost, which one costs more? The electronics, which is what? The cross points, or the cost of what? Memory. The cost of memory is smaller and smaller and smaller. Its effect is what? Is less than the effect of what? The number of cross. So they usually divide it by what? 100 to make their what? Effect smaller than what? Than the number of cross points. Did you get this or not? Okay, I will tell you what? I will tell you ignore this 100. In other words, I will tell you find them separately. Find the number of cross points, data memory, bits for both the data memory and the what? And the control memory. Okay, let's see if you can help me here. This is what? What is this? This is we have a what? A T by T, TST. We have TST. Let's understand first of all the times and then the space switches. These are the time switches. What does N by K means? When I say N, does it have 1 input and what? 1 output. How many time slots at the input? Here we do have what? Time slots. And how many time slots in here? We have K time slots. Okay. Now, time switch, I will explain to you what I mean by time shared in a minute. The space switch does not a switch slots, which means what? If there are what? K time slots in here, how many time slots do we have here? K, also K time slots. Did you understand that? Yes? No response. The space time slot. Okay. In here, how many time slots do we have here? K. How many time slots do we have here? Slots. Did you get this or not? So let's take an example. Suppose this one, this wants to communicate with this. what do I do? Let's see what I do. Okay, now this can be switched to what? Switch to here. Are you following me or not? Okay, this one, where does it have to be switched? It has to be switched in here. No, no. So this one is switched in this space to here. Is switched in what? In time to here. Clear? Okay. Now for this switch, again, for this switch to be non-blocking, K has to be greater than or equal to what? To 2n minus 1. This one to you a moment ago. K, which is what? What is K? K is the number of time slots in here, whereas this one time slots in here. There is a typo here. This one should be what? N by n. Clear? Clear? Okay. Have here n time slots. How many total do we have? N. Are you following me or not? It means how many units in here do I need? How many time slots unit? Time slot interchange. This is a time. Whereas this one is a what? Space switch. Let's calculate the complexity. I want you to understand one thing here. Time slot. During the first time, why do I call this one time share? Is it the same space switch? That is the same space switch. During the time slot, during the first, this switch needs to be configured such that it switches the first time slot of inputs to a what? To the first time slot in every one of the outputs. One more time. This switch time slot. It switches in space. every one of these time slots, the first time slots, needs to be what? Needs to be connected to what? To every, which time slot? First time slot at the output of the space switch. Clear? Okay. In this, the second time slots will go what? Will go in different ways. So the space switch needs to be what? Did you get this or not? The connectivity inside the space switch needs to be what? Changed or not? But is it the same switch? It is the same switch, and that's why we call it what? Time shared. You switch in what? In time. It's the same switch, but the configuration will change every what? Every clear? Configuration of the switch will change every time slot. I'm not sure you are getting the point. Configuration change every time slot. Are you getting this point? During the first time slot. During the first time slot. Yes? Where is it going to? It's going to what? By the way, this time slot, first one, does it belong to the same user? It does not user. You follow me or not? They are each going to certain what? To the certain first time slot. Does not switch in time. First time slot in the output. Did you get this or not? Okay. Do they belong to the same users? No. Are they? Is it possible that the second one is going here? And the configurations of the switch needs to be what? Needs to be changed. The configuration means what? The connected switch needs to be changed. Clear? Clear? Okay. Let's see if you can help me. Complexity. Of a TST switch. First of all, points. How many? Still waiting. Numbers. How many? Remember, when you talk about cross points, which one are you talking about? The time or the space? Space. Time does not have cross points. Did you get this or not? How many cross points do I need? N squared. Yes? Yes. Data memory. Number of bits in the data memory of time. Okay, assume every slot L bits. Assume every slot has L bits. In a T1, how many bits do we have? In a T1, how many bits does it have? Oh God, 8. 8 times general. Let's assume that it's what? L bits long. Yes? How many do I need? How many do I need? Here. Let's look at this one. How many time slots do I need? How many time slots is there? Here, you are going to what? Write into the memory in a sequential fashion. How many do we have? Yes or no? So what do I have? N. How many each one of them? How many bits does it have? L. Are you? Yes or no? Continue. Continue. These do I have? N of them. N of them? Of them. Yes or no? So what do I do? You didn't get it. It's so frustrating. You are not getting it. How many time slots do we have here? N time slots. Yes? You need to write it into the memory. So, for example, this one here, how many is it going to occupy? How many? L bits. How many time slots do we have? N time slots. N small. Yes? So each one of them will have what? N times what? L. Yes or no? We have total. And 2 times what? Did you get it or not? Yes or no? Okay, this is the number of. Now, let's see if you can help me. Number of bits in what? In the control memory of the time switch. Help me. The control. The control. Now, the control is what? How many times? K. Yes? How many bits do I need? The control is just a what? A pointer toward what? Towards the location that will go to the appropriate time slot at the output. At the output do we have? K. Yes? Yes? What is the address do I need? Log what? K. Yes? Log what? Why you are not getting this? How many locations do I have here? How many locations do I have? The first location, the second location, third location, fourth location, 5th location. How many location, small n location. How many bits do I need to address these locations? How many bits do I need to address log what? N. This is log n. Yes or no? Time slots in here, there are. K time slots. So this is the K. Yes or no? Okay. How many N, how many T stages do I have? 2. So there's 2. Did you get this or not? Did you get this or not? Okay. Bits. In the control memory of the space switch. Help me. In the space switch, do we need a control memory? Do we need a control memory? We need a control memory. Why? I told you the space switch what? Configuration every what? Every time slots. Did you get this or not? How many time slots? How many time slots? We have K time slots. How many inputs do we have? N. Yes? All memory is going to what? To point to certain location. Yes? How many addresses do we need? And the addresses do we need? Log what? Which N? Small n. Capital N. Did you get this or not? You are not getting this here. You are not getting it. It's so frustrating here. How there in this switch? This is N by what? N. Agree? First time slot. During the first time slot, the control memory needs to what? Needs to what? needs how many to configure this one here? Log n. Yes or no? Okay. It needs to repeat that every what? These time slots. How many time slots do we have? K. This is the K. Did you get this or not? Did it have? This is the N. Did you get it or not? Yes or no? This requires in the control memory. So the total is what? Total cost is what? Is n squared plus what? 2n plus 2n k log n plus what? K log n over what? Over 100. Clear? Oh, now ask you, okay, try at home to find the complexity of an S switch. STS means what? What does STS mean? Space, time, space switches. Which means what? It means that what is a space switch? Yes. Second stages are what? Third stage is a what? Is a space switch. And compare it with this one. And compare with the TST. I might give you this in the midterm. So make sure that you do understand how you do it. Clear? Okay, if this one is not to see me after the class. I have spent too much time on this already. Too much time, way too much time. Okay, good. So if you are still having doubts with this, see me after the class. Did you understand by time shared? Time shared means what? It's the same switch, but I will change the configuration of every what? Every time slot. Every time slot. This time slot, I'm going to change the configuration of the switch. Time slots, I will change the configuration of the switch. It's the same physical switch, but the configuration, the connectivity are going to what? Are clear? So we call it what? Time share. Okay. Now let's look at the buffering here. Buffering in switches could be what? In the input, or it could be what? At the output. Buffering means what? Means the Q. It could be in the input, it could be at the output, or it could be in what? In both. But at the what? Non-buffered ATM. Non-buffered switch, N by N. This is what you can, it's a crossbar ATM switches. Clear? When we talk about ATM switches, just keep in mind all of the fixed, the cells, the time slots are all of the fixed duration. Clear? Duration. Cell is the same. Clear? Okay. So now, let's see if you can help me understand this one here. I have an N by N crossbar, but there is no buffer. There is no buffer, which means the following. Let's see if you can help. Does it have N inputs? How many outputs does it have? N outputs. Is it possible that we are going... Contention means what? Contention means what? They are competing with it. You can help me here. The first time slot in here is destined to here. The first time slot in here is the same location. Did you get my point or not? Is there a contention? There is a contention. One cell will survive, the other one will be what? Disregarded. Why the other one will be disregarded? What disregarded means? Means dropped. Why? Because there is no what? Non-buffered. There is no non-buffered in here. Are you following me or not? Okay. Now, how do we calculate the probability? How do we calculate the probability of this happening? Did you get my point or not? There is no buffer in here. So if there is a time slot in here that are destined to the same output, one of them will survive, the other one will be what? Will be clear, will be dropped. Let's understand what is the probability of this happening here. Let's go. The cells arrives in a time slot with a probability of what? P. Which means what? Every time slot, probability of P that there is a what? A cell, and there is a probability of what? 1 minus there is no cell. Did you get this or not? Okay. A given input has a cell present with a probability. Cells in different time slots are assumed to be generated what? Independently. Which means what? the time slot there is a cell has nothing to do with what? With whether there is a cell in the next time slot. Time slots are what? Are independent. Traffic is uniformly distributed across all. In other words, there is no one line that is what? Heavier than another line. All the lines are really likely to have a cell in it. A cell is equally likely to be switched to any outgoing. A cell in here is equally likely to be what? Going to any one of these ports. Did you get this or not? And each cell occupies a what? A time slot. The duration of the time slot is the same as the duration of what? So let's assume that the time slot has a duration of what? T, capital T. Did you get this or not? Okay. What is the probability that a given input has a cell destined to a given output? Consider what? Consider this output. Yes? What is the probability that there is a cell in a given, for a given what is the probability that a given input line has for a given output line? It's what? P over what? N. Why is it P over N? P is there is a cell, and 1 over N is the probability that it will be destined to what? Particular output. Why is it 1 over N? It's 1 over N because we said that every cell is equally destined to any other output. How many outputs do we have? N outputs. What is the probability? If they are equal, the probability that the cell will be coming here or here or here or here. It's 1 over N. So it's what? P over N. What is the probability that one cell in any given time slot, what is the probability? Is a cell. What is the probability that there is a cell in a given time slot at that output, at that particular output? What is it? Let's see if you can help me. When will there be a cell? When will there be a cell in a given time slot at a given output? Let's look at this output. Output 2. Just an example. Output 2. When will there be? How are you going to do? And this will be included. This will be included in the midterm. Do you understand this? Okay, good. We understand each other. Look at this outgoing. Look at this outlet. Yes? Probability that there is a cell. What should happen such that there is a cell here? That should be what? At least one cell in here into what? To that particular output. At least one of them. Why? Because if there are 2 of them, or of them, what will happen? Contention will happen. Yes? Only one will go. The others are what? Disregarded. Did you get this or not? So at least one of them is destined to particular output. Yes? At least one of them. What is it? What is 1 minus to the n? P divided by n. What is this is giving you? Minus P over n is the probability that none of the are destined to what? To that particular output. Did you get this or not? Okay, why am I raising it to the power for all of them? Did you get this or not? Yes? And why am I subtracting? Because I want what? What is the probability that there is a cell? Did you understand? Everybody got it? Okay, good. So, what do we have here is what? Now, what is the throughput? This is what? There is a cell, the probability that this output. What is the throughput? The throughput which is measured in what? In cells per second. At that particular output, what is it? It's this, which is what? Which is the probability that there is a cell divided by what? Divided by the cell duration. Clear? Or the time slot duration. What does the throughput mean? The word throughput. What does it mean? Throughput means what? That there is a cell. If there is no cell in here, it means what? There is no throughput. There is a cell here means what? You got to throw this switch. This or not? One more time. One more time. What am I looking at in here? I'm looking at a particular what? Output. Look at a particular output. See that there is a cell. What is the probability that there is a cell? To have a cell in here, do I need? I need to have at least one of the input having a what? A cell sent to what? To that particular output. Yes? At least one of them. Why? More than one, what will we have? We have contention. One of them will get through, which means what? A time up. And the others are what? Disregarded. Yes? So when we say at least, I took then, which is what? 1 minus P over what? N. What is 1 minus P over N? N, it means what? There is no what? In here, destined to what? To that particular output. Yes? Okay. Why did I raise it to the power N? So all of them? Yes or no? And why did I subtract from 1? I subtract from 1 the probability that there is a cell. This one here is what? Is the probability that there are no cells. This or no? When I subtract from 1, it means what? The probability that there is a cell. And then I divide by what? Clear? Okay. Now, the maximum throughput appears when P equal to what? Equal to 1. What is P? P is the probability that there is a cell. Clear? The probability that there is a cell. Clear? Okay. When you plug in P equal to 1, you will get the maximum throughput to be what? 0.63 divided P. What is, by the way, what is the ultimate throughput equal to? What is the ultimate to? 1 over what? 1 over T for each particular output. Not the switching to what the switch throughput means. This one is for a particular output. What is the throughput, maximum throughput? 1 over what? T. 1 cell per what? Per T. Did you get this or not? Yes? How much did we get? If P is what? If P is equal to 1, which is the best throughput, we get what? 3 over what? Over T. That's the throughput. Clear? From what? A particular output. Why do I multiply by N? This is what? The switch is the throughput of the switch, of the entire switch. Clear? Okay, good. Now, let's look now. I'm switching with input queuing. Now we have what? And rather than what? An output queue. So input queued, we will call it what? I. Q stands for what? Input. Let's see if you can help me with a problem in here. The problem, by the way, we will call it what? We head of line blocking. Let's see if you can help me understand what is the head of line blocking here. Look at the following situation. Would you understand what this means? 2, 0, 2, 1. What does it mean? There is a cell in here that is destined to which output? 2. This one is destined to which output? This one is destined to which output? 2. This one is destined to which output? 1. Did you get to determine? This is at the start of cycle 1. Start of cycle 2. What happens? The 2, yes? Okay. Now this one and this one are destined to the same out. One of them will be what? Blocked. Are you following? Sorry, one of them will be what? Queued. Not going to be what? Dropped. Like the one I showed you a moment ago. The one that I showed you a moment ago, there was no what? Buffer. And here there is a what? Buffer. So what did I do? Look at what I do. What happened? Is it still at the input? Is this one? Is it still at? Yeah. Okay. Now, was the 0 switched? The 0 switched. Was the 1 switched? 1 is switched. Did you understand this? Now, at this time, what happened? Another time slot came. Yes? And here also. Let me ask you a question. This 3 and this 0, did they come at the same time? But this one happens to be after the what? The 2. The 2 is what? Is sitting here. No. Okay. The 3, this is 3. Could it be switched? Yes. They switched. Yes? Now, I want you to tell me something. The 0 here, is this one available? This one is available, but could it be switched? No. Why? Because it got what? By the one which is what? Ahead of it, even though the output, which is number what? 0, is what? Available. It's free. Yes or no? Are you getting the point or not? Even though number 0 is what? Is free. What? It got blocked. We call it what? Ahead of line what? Ahead of a line blocking. My point or not? Yes or no? Okay. So what happens? This one has to wait until what cycle? Because in this current cycle, the 2, where did the 2 go? Where did the 2 go? This 2 was, did you get this or not? This 2, by the way, is This 2 is already what? Is already gone. This one is the content of this guy. Same is blocked. Clear? Clear? Okay. Now, if we do the analysis, we will see that the maximum throughput of an input queued is actually what? It's actually what? Less than the previous one, which is what? 0.586. Can you tell me why? Intuitively, why the throughput came down? The throughput came down because what? The time to what? To serve each individual cell is going to be what? Increased if there is a what? If the blocking, which means what? The throughput will go what? Will go down. Did you understand what I just said or not? Okay, it's loss model. In the previous one, if there is contention, the cell is going to be what? Dropped. There is no, whereas in here, if there is a head of line blocking, the cell will wait its turn to be what? To be clear? Okay, good. The switch speed is the same as the line speed. Can you tell me why the switch speed is the same as the line speed? The switch speed is what? As the line speed. One read and one write per time slot. Did you get this or not? As opposed to the other one. Why? This one. Sorry. This one and this one. Can they be switched at the same time? Them will be what? Blocked. The other one, blocked means what? Queued. The other one will go through. Did you get this or not? So this one does not. It's twice as fast. Did you or not? Because only one of them will go what? Will go through. Clear? You will see the difference between this one and it. Okay. Now, before we do the analysis, I'll get back to this in just a second. So that you understand the similarity between the two. I'll get back to the analysis head of line blocking in a minute. I want to show you now the outgoing queue. Now, this is OQ. OQ means, what does OQ means? Outgoing queue, which means the queue is way at the output. What does that imply? If there are two cells, listen to me, at the inputs, which are destined to the same what? Output. Both of these switch to what? To the output at the same time. Did you get this or not? We what? Served, and the other one will wait where? At the output queue. Or not? Not sure. Did you get my point here? Let's take the same scenario. What do I have here? 2, 0, 2, 1. Do you understand the notation numbers mean? This is here. This here. This here. Yes? This is, what is the start of cycle 2? What does it look like? Was the 0 switched? Yeah, okay. Was the 2 switched? Both of them. Both of them were switched. Which means what? 2. This is the first 2. Where is this one sitting? At the output queue. At the output queue. Both of them were what? Switched. Did you get this or not? Okay. Cycle. What do you have here? 3, 0. Yes? This one will be switched. This one will be switched to 0. What is this one? Can you tell me what is this one? This one will be what? Served. Is there a head of line blocking? There is no head of line blocking. But does the switch needs to work? Why? Why does the switch needs to be working faster? I'm not sure you are. Why does the switch needs to work faster? Because both of these cells needs to be at the same time. Are you following me or not? Whereas in the previous case, the what? When we have two cells destined to the same output, only what is a switch? The other one is queued. Clear? Okay. So let's see if you. I'll get back to these charts. Okay. Why is this one not in the same? Did you understand the difference? We'll get to the analysis in just a second. Did you understand the difference between the two? Okay, let's go back to the, okay, let's understand this. Let's see if you can help me with this. The head of line have a what? A 2x2 switch. So the switch is a what? Is a 2x2. This is a switch. How many connectivities can I have if it is a 2x2 switch? It could be like this. Yes or no? Or it could be like this. Clear? Clear? These are the two states. And the switch can either switch this one to this one, this one to this one, or this one to this one, this one to this one. Now, let's see, understand the notation here. What do I have here? This is the input. What do I have? 0, 1, 0, 2, 0, 2. Input 2, 0, 1, 0, 2, 0, 1. Okay, I want you to understand this here. What does this mean? 0, 1, 0, 1, which means what? That is destined to what? Outgoing 1. Do we have a cell at the output? Cell at the output. The other one will be what? Queued at the what? At the input. Did you get this or not? Why is this one here? 0, 1, 0, 2. Both of them got it through. Did you get this or not? 1, 2 to 1. 2. Same thing. Yes? 0, 2, 0, 2. 1 and the other one is what? Acute. Did you get my point or not? Yes or no? You can help me. Is that the write the probability of each one of these states? Let's see if you can understand the state diagram here. Let me see if you can help me here. Okay, what is this? Let's see if you can help me. Are in a state 0, 1, 0, 1, then one of the packets will be what? Are you following or not? The probability that it is replaced by a 1, 0, 1 packet. Will you answer what replace me? Replace that, the one that was what? That is delivered. Yes or no? What is the probability that the probability that it is replaced by a 0, 1 point what? It's 0.5. Why? Why is it 0.5? The next one is either what? That particular output or what? Not destined to that particular output. So what do I have here? What are the states? Different states. What are they? 0, 1. This one is what? 0, 1. This one is what? 0. Yes? One more time. If you are in state 0, 1, what does it mean? When I say 0, 1, 0, 1, what does it mean? This is the input 1 and the input what? 2. Yes? So you could have what? 0, 1, 0, 1, 0, 2, 0, 2, 0, 2, 0, 2. If you are in 0, 1, 0, 1, then what? One is delivered. Yes? Where is the other one? The other one is queued. Yes? That the one that is delivered is replaced by what? Another 1, 0, 1. Did you get this or not? Yes? What is that? That's 1/5, 1/2. By 0, 2 packet is also what? Is 0.5. Now, it will move to 0, 1, 0, 1 with a probability of what? 0.5. It will move to 0, 0, 1 with a probability of what? 0.25 and 0, 1, 0 to probability of what? 0.25 also. So this one and this one, 1/4, 1/4. Did you understand that? Did you get this one or explain this one to me? What is this one? Why is this 1/4, 1/4, 1/4, 1/4? This is 0, 1, 0, 2. What is the next state? What it could be the next state? If it is 0, 1, the next state could be what? 0, 1, 0, 1. Yes? What? It's, by the way, when I say 0, 1, 0, 1, what does it mean? The one that replaced 0, 2 is what? Is 0, 1. Destined to which output? The first output. Did you get this or not? Okay. What? 0, 2. What did we say this one is? 0, 1, 0, 2. This one is what? 0, 2, 0, 1. Yes? Why is this one? Can you explain to me why is this one 1/4? By the way, the sum of the probabilities in each one of them has to be equal to what? Has to be equal to 1. So if
the time
you
is
are
22 o'clock.
Explain this one to me. Why is this one 0? Is it 0? You cannot, huh? 0, 1, 0, 1 to what? 0, 2, 0, 2. Do you understand? Yes? Similarly to here. Why is this one 0? You cannot go from what? To 0, 2 to what? 0, 1, 0, 1. Did you get this or not? Okay. Transition matrix. Can we write the steady state probabilities? We can write the steady state probabilities. Let's see. What is it? What is the steady state probabilities? This is 503. What is it? It's P 0, 0. What did we say? Sorry. 0, 0, 1. 0, 1. Yes? P 0, 1. 0, 2. P 0, 1. 2, 0, 1. P 0, 2. 0, 2 is equal to what? The same times what? P. This P is this P. Did you get this or not? Okay. And if you calculate what? If you calculate the steady state probabilities, what do you get? You get 1/4, 1/4. Each one of them is equal to what? 1/4. Clear? By the way, you don't even need to do this analysis to figure out this 1/4, 1/4. If you see the probability matrix, if the sum of each row is the same as the sum of each what? Both of them are equal to what? 1. The matrix is referred to as what? Double is the answer is what? Is that the probabilities will all be what? Will all be the same. And since we have how many states? We end up with each one is what? 1/4. Now, if it is 1/4, what is the throughput? If it is 1/4, in other words, the probability of this is what? 1/4. The probability of this is 1/4. The probability of this is 1/4. Yes? What is the total for output 1? Output 1, remember, there is a what? Cell here. There is a cell here. There is no cell here. Why there is no cell here? There is no cell here because they are destined to the second output. Did you? So what is the throughput? 0. Time slot. Did you get my point or not? Yes or no? It's 0.7. Why? Because there is no about this one. Also the same thing. Clear? This is a 2 by 2. If you increase the switch, in other words, 3 by 3 or 4 by 4 or 5 by 5, the probable output will drop all the way to what? 0.586 divided by what? T. This one is what? Is it? What was it? 0.75 over T. This is 0.75. Clear? Clear? I'm not sure. Did you get this? Did you get this? This transition. This one. Did you understand? Okay, good. For n large, and here we took n is what? In this case, it's 2. But for n large, we can do also the analysis using what? Using the Poisson assay. Large, let Ki represent the set of inputs that have a packet destined to output I. Out of Ki, only what? Only, this is an input queue. Only one input. All the others are going to be what? Queued at the input. Clear? Okay. So for large n, let K set of inputs that have a packet destined to a particular output. Okay. N is the sum of what? Is the sum of Ki. Why is it the sum of Ki? N. N is the number of inputs. Yes? Yes or no? We say the sum of Ki, what does it mean? Some cells are destined to this output. Some cells are destined, and so on and so forth. The sum of them is what? N. We can write the equation for the evolution of what? Ki. What is Ki? Is the number of what? The number of cells waiting in input boxes or not? What is it? Let's see if you, by the way, we have seen this when we're talking about what? The buffer management, the evolution of the queue. What do we have here? Ki t plus 1 is the sum of what? What is Ki of t plus 1? Means at t equal to what? At time t plus next cycle. Okay, what is it? Is the maximum of Ki. Why is it minus 1? One of them is gone. Did you get this or not? Plus Vi 1. What is this? That's a new arrival. Did you get to that particular what? output. Yes? Because where is that going to go? That is going to go in the queue, in the input queue. It has to wait. It's clear. Did you get this or not? So where plus one is the number of destination IP packets moving into the what? The head of line position in a slot what? T plus 1. The head of line position in a slot T plus 1. For large N, the I will be what? Lambda I, which is what? Which is the average rate. And the actual process can be a Poisson. And you end up with a Q, which is identical to what? MD1. Why is it MD1? Why is it MD1? Variables are what? Are Poisson. The service is what? Deterministic. Why the service is deterministic? The service is deterministic because we are dealing with what? Fixed size cells. Yes? And all what? Only one of them will get served. So we have a what? A single server here. Clear? So at the queue, what? As an MD1 queue. Clear? Okay, good. Now, this, you already have seen all of these equations in the case of what? In the case of the MAI, which is what? Which is a number. This is the average number. Average of number of average number of packets, and we from before we derived this equation for the MD1. You can check it and review your notes. And for the uniform case, you know what? Every packet is destined to every outgoing. Every packet has equal going into a given output. The N will be what? Will be the summation of this guy over all I, and when you solve for lambda, you will end up with what? So equal sign. No, equal. You will get the point. Put equal sign here, equal sign here. Both of them are equal sign. You will end up with what? 0.586 and 0.586 by T. All of these equations we have already derived. Earlier in the semester. But when we derived it as what? MG1. But in this case, the G is deterministic. Did you get this or not? So review the equations and you will end up with this equation. Very easy to see. Okay. Now, let's get back to the, what happened here? Outgoing queue. Okay, the outgoing queue. Again, this one needs to be switched what? Needs to be switched at the same time. Cells will be joining an outgoing queue. Clear? Okay. Let's do the analysis for this one. This is again, these are the queue at the output. They are going to be switched in here, waiting their turn in the what? In this case here, by the way, what do I have? For each one of them, there is a queue. In here, what do I have? Shared memory. Are you following? Queues are what? Are sharing the same memory. This one, there is a queue for each what? For each output. Memory for each output. This one, they are sharing. Yes? Sharing the same memory. All the outputs are sharing the same memory. Did you get this or not? Let's do the analysis. First of all, the basic OQ switch. You can help me. The maximum memory bandwidth required for the the bandwidth is 2. Explain to me 2NR. Let's look at first of all at the assumption. Consider an outgoing queue switch with n different physical memories. N different physical memories means what? These. N different physical memories. And all the links are operating at what rate? At a rate of R bits per what? The links. In the worst case scenario, cells may arrive simultaneously. All inputs destined to what? Just one out. All of them needs to be switched at the same time. Which means what is the maximum switching required? R. Did you understand why it is NR? Is it possible that there is a cell here, a cell here, a cell here, all destined to that output? The switch needs to what? Each one is coming at what rate? The cells are coming at a rate of what? R cells second. The switch needs to work what? Faster as what? The sum of them. Why? Because they are all going in time. So it's what? It's NR. Yes? Now, for the shared memory switch, shared memory means what? This one. Can you explain to me why it is 2NR? For a shared memory switch, this one they are going to go to where? Here. Going to go to here directly. Did you get this or not? In a shared memory, what do I have? I need to what? Write it into the memory and then what? Read it out of the memory. Did you get this or not? Because the memory is what? Shared. The locations are what? Are shared. In here, it is what? Every one of them have a separate what? A separate queue. Did you get this or not? Yes or no? This one. Every one of them have a separate, when the what? When the cells in here coming in here, they are going to be switched to that queue. In here, they need to turn into a memory and then what? Read from the memory to a particular output. Clear? So this speed should be what? Should be 2 NR. Now, let's do the analysis. When 2 or more cells are destined, 2 or more cells at where? At the input, are destined to the same output line, all the cells will do the switch. All of them will be what? Switched. One of the cells will be put on, others will join a what? The outgoing queue, which means what? I don't have a head of line blocking. Can help me with the analysis. The output line rate, same as what? The input line rate. Can you tell me why? Only one of the cells will be what? Will be served. Did you get this or not? So the rate is equal to what? Input line rate. The switching rate. What is it? Switching rate. Again, assuming that each one has individual queue. What is the switching rate? N times what rate? Why? Why? There is a possibility that there are what? All the input lines are destined to the same what? Output. He should be able to switch all of them simultaneously. So it's 2 NR. Let X be the number of cells transferred to output during any one cell interval. So during one cell interval, during this cell, let X be the number of cells transferred to a specific output, any output, pick any output of any, during any particular cell. What is the probability of X equal to K? Variable. What is the probability that X is equal to K? And choose what? K. Did you answer what? N choose K? And how many input lines? N choose K times what? The probability that there is a cell destined to that particular output. What is that? P over N. Question, why is it P over N? P is the probability that there is a cell times 1, which is the probability that this cell is what? Headed to that particular output. Raised to the power what? K is what? Raised to the power what? And one here like this. This is the same as this one. Did you get this or not? And K is equal to all the way to what? N. What does K equal to 0 means? When I say K equal to 0, what does it mean? There's no cell destined to what? That particular output. Okay. Say that again? Oh, thank you. Okay. What is E of X? By the way, when N approaches infinity, you all know what? You all know that is this binomial? This is binomial. What is E of X? E of X for a binomial. It's what? N times what? Binomial. If I tell you N, choose K, 1 minus P to the N minus K. Yes? What is the average? NP. It applies N, this small n. It's capital N. What is this? It's P over what? So E of X is equal to what? N times what? Which is what? P. And as P infinity, as P approaches, I said P approaches infinity, I'm sorry. As P approaches what? Probability cannot be more than 1. As P approaches 1, what is the maximum throughput? What is that? As P approaches 1. Remember, what are we talking about? E of X is transferred to a specific what? Output. As P approaches 1, watch. 1 over T. Is this the ultimate throughput? That's the ultimate throughput. Is that compared to what? Compared to the input queued. What was the input queued? What was the throughput of the input queued? 1 over T, it was what? 0.586 over T. Yes? How much was it? 0.6 something. Yes, over T. This one is what? 1 over T. Switches are what? Are outgoing queued. Did you get this or not? But the problem with the outgoing queued is what? Is what? It's not what? Scalable. The switch needs faster n times what? The rate of each incoming line. So as the number of what? Number of incoming lines increases, this working much faster. Did you get this or not? Did you get this or not? So let's stop here. Not the lecture. Let's stop the material here. The material is included. And I will definitely give you questions on this, more than one. So you better understand what I just did. Clear? Now, let's look at different types of switches, which is called routing switches, self-routing switches. What does self-routing switches mean? Those switches that does not, in the header of the cells, we will give them information of where to take the cells. Where to take the cells. So for example, a switching element, examine the next bit of the address of what? Several bits. Next bit of the address. If it is 0, then he will switch it what? As 1, he will switch it what? Downward. Did you get this or not? Okay, so what do we have here? Look at the output in this case here is what? By the way, we do have different types of switches. We have omega switches, ion switches, we have the delta switches. All of them differ from each other. Look at how they differ from the connectivities between the switches. Look at this one and look at this one. This one is different than this. This is different than this. So not. Okay, so for example, in here, this one and this one. This goes to this and this. So it's what? Alternate. The connectivity alternates. This one and the second one. This one. Third, fourth. This one. First, second. This one. Did you get this or not? And repeat. Whereas this one is what? What is this? This is going to what? 3. This one is going to what? 2, 4. This one, 1, 3. This, 2, 4. Yes or no? Okay. How about this one? 1, 1, 3, 1, 3, 4, 2, 4. But in here it's what? 1, 1, 2, 3, 4, 3, 4. Okay. Now, what are these? What are these? 0, 0, 0, 0, 0, 1. What? Let's see it here better. Okay. Can you zoom back, please, a little bit? Okay. Okay. We'll continue with this next time. Clear?